Hi there, this is Jacob Nash, Algebra Lessons, and this is Unit 7, Lesson 8. This is on transformations of can't even say that. I could really just say logarithm functions, but I had to say logarithmic functions, whatever. So this is pretty much the same as Lesson 5 that we had. It's just instead of exponential functions, we have logarithm functions. And here is our basic equation. Now this isn't the parent function. Remember, our parent function was we had y equals well, we said that it could be this, but if you really want to have a value in there, then we can just say this. That is what it has. So we can see that, okay, that's not good. This thing is so annoying. I wish I could just make all of those tabs go away. I don't know what happens. So we can see that 2 is to be here. I don't know why. Just drew like that. And x, it is everything in here. So that's how that's translating. But you can have, basically, these things are things that can change. So while we originally have the log b x, you can do something with a, c, h, and k. Let's see what those things are. I have a nice table of values that say what the transformation is, what's the result, and what's the operation. Okay, so let me try to zoom out so you can see the whole thing. Alright? And we have 2 asterisks. We'll talk about that in a minute. That's just something I want you to keep in mind. So if a or c are 1, what happens? Normal. Nothing is there. So if you don't see anything, then a and c are 1, which is what the case is in the parent function. And operation is nothing, obviously, because it is nothing. So h and k, if they're 0, then there's nothing there. Because we know why this makes sense. Anything times 1 is itself. Anything plus or minus 0 is itself. So that makes sense. So nothing is there. Same thing with h and k if they were 0. If a is greater than 1, we have a vertical stretch. Vertical stretch. Keep in mind that I said vertical, not horizontal, because there are horizontal stretches. So what that means is that the y values happen more frequently, causing the arc of the graph to change. We'll see what that looks like in a minute. And operation, that just means what do you do to the values. You're either changing something to the x or changing something to the y. If you have vertical stretch, you multiply the y values by what a is. Ow. I accidentally just hit my thumb with something. If a is in between 0 and 1, so if it's like 1 over 2, 1 over 4, something like that, then it's a vertical compression. It doesn't matter. You still multiply the y values by a. Then, if you have c, which a basically is just something that's not in the parentheses. C is if it's right beside x. If that value is greater than 1, then it's a horizontal compression. Okay, asterisk, let's see. Different than what you might think. Oh, what do I mean by that? Well, when a was greater than 1, we had a stretch. When c is greater than 1, it's a compression. So don't get mixed up. You might think, oh, if anything's greater than 1, stretch. Nope, that's not the case for that one. Why? Because it's in the logarithm function itself. We're taking the logarithm of what's in there. So that's making it reversed because it's the inverse function. If c is in between 0 and 1, then we have the horizontal stretch. And for both of those, you just multiply x by, that says a, it's supposed to be c, sorry. X by c. Once again, sometimes I copy and paste things and forget to change them. Then, if the h and k are the same as what we've had for rational, radical, quadratic, exponential, same. Left. If you have plus h, that means left h units. So you do x minus h. If you have negative h, or something x minus h, then that means you go right whatever h is, units, and then, like I said, I have an asterisk by that because remember that might be different than you think. Left is positive, right is negative. But in the end result, you add values, you add h to the x values if it's going to the right, and you subtract it if it's going to the left. If k is positive, then you go up k units. And once again, I have the wrong things here. It's supposed to be plus k and then minus k. Sorry about that. Down if k is negative, that's the same, so I'm not going to go in complete depth with that. If a is negative, you have a reflection over the x-axis. You have a reflection over the x-axis. But what that does is makes the y values negative, not the x. Just because we're reflecting over the x-axis doesn't mean that makes the x values negative. So I really should have put asterisks there. If c is negative, then you reflect over the y-axis and you make the x values, if you make them negative. Then we have b. So b is our base. Now let's talk about what things can happen if that's changed. So if whatever b is, so if, let's just say b is n. In this case, for the parent function, n is 2 and n is b. So b is 2. So don't get confused by that. But basically, whatever b is the x value of a point that has the y value of 1. So basically, if you were making a table, if y is 1, x is b. So whatever the base is will be the x value of the point where y is 1. That's what I'm trying to say. And I have a blue asterisk because keep in mind of any transformations. That only holds true if there's no up or down or left or right transformations. If you have h plus 2, it affects it if there's a left or right function. If you had h, which was positive 2, then that means you would do minus 2. So if the base was 2, basically what I'm saying, we'll see this later on, but if you have this, where you have a, we'll just make it like this. Log, we have 2, and then this is our function. So that means we go left 2, and we know that since there's 2, we have a point of 2, 1. But since we're going left 2, it's not going to be this. So this rule only holds true if there's no transformations, but it's just something to keep in mind. Then these are not commonly observed in Algebra 2, but if b is greater than 1, then it flattens the graph. And I can't really explain what the operation is right now. And if it's in between 0 and 1, you'll notice that it reflects over the x-axis and still flattens it. So it's kind of complicated, but it's not something you really look at. So we're just assuming that b is constant. In most cases, you'll see it as 2. We're really focused on what a, c, h, and k are. So now let's look at examples, finally. So red is the parent function of log with the base of 2 of x. So we have 5 different examples here, and let's see. Okay. So for this one, we need to see, based from the parent function, what has changed. We have minus 1, and it's in the parentheses. So what does that mean? If it's in the parentheses, that means that we have right 1. Oh, well, I don't need to write that there. That's why I made a transformation section. So let's just zoom this in and say right 1. That's what we're doing. And therefore, what's the operation? We're going to add 1 to the x values. That's all we're doing. That's the only transformation there is. So here are the original x and y values. We need to see what happens after the transformation, and then we'll plot these points. So nothing happens to the y values, so let's just keep them the same. and we need to add 1 to the x value since we went right 1. That would mean that we have a 1.5 here, and then really 3 halves, but we can just say that. Then we have 2, and then we have 3. So we need to plot those points on the graph. 1.5, negative 1. 1.5, negative 1. Then we have 2, 0. Then we have 3, 1, right? Wasn't that one? Okay. 3, 1. Now, before I go on, what is b? In this case, we have b is 2. b is 2. So that means I said that when there's 1 for the y value, whatever the base is what it is. So we should have the point 2, 1. But why don't we? It's because of the transformation we had that was minus 1. So if we need to do minus 1 for the value, which actually, sorry, it says minus 1 here, but that since that means going right, if you were to set x minus 1 equal to 0, we'd find that x is positive 1. So you add 1 to the x values. Since we added 1 to the x values, that changed to 3, 1. And that is a point we just plotted, so that makes sense. So now, we haven't plotted a whole lot of points, but we can just kind of guess where this is going by what the red does. It has an asymptote right here, so it should do about the same thing till it gets right here. And then it does about like that. So that's the difference. Well, really, it would be kind of more like this. So that's what happens. Since we had right 1, we can see that the graph shifted right 1. All right, here's 1. What's different? We have a plus 5 not in the parentheses, so that means up 5. So that's our transformations, up 5. That means we add 5 to the y values. X values are staying the same, so let's keep them the same. And then add 5 to the y values. So that would be 4, that would be 5, that would be 6. So 1/2 4, or 0.54, is going to be right here. Then 1/5, it's going to be right here. And then we have 2/6. Oh, okay, so I actually realized I forgot to say something about up here. Realistically, I forgot to say, this is not graphed correctly because since we had, remember for the exponential functions, the vertical or the horizontal asymptote could move if there was a transformation up or down. Since this is inverse, if there's a transformation left or right, which there was, that horizontal or vertical asymptote moves. So since we had minus 1, that means that the asymptote is going to move right 1. So it's going to be right here. So that was not graphed correctly. Didn't mean to erase the points though, so got to see that again. 1.5, negative 1. I can remember the others, 2, 0, 3, 1. Okay, that's not the best, but we're trying. So it's about like that. Sorry, forgot to say that. That's kind of important. For this one, we're not going to have an asymptote change just because it was an up or down transformation. So now we're going to draw it. Okay, terrible. I hate when it does that. Alright, now let's try this again. Alright, that's not a completely accurate drawing, but that's around what it would look like. Move on to the next one. What has changed? Oh, we see that we have our A value changing to 3. We can tell that's our A and not the C because it's not in the parentheses. Oh gosh. it did that thing again where I wanted to undo and then it took forever and then undid every other thing. Okay, since that's there, that means we have our x values that need to, or y values, sorry. That means we have a vertical stretch, which means y values multiplied by 3, because that's what it was. X values are staying the same, we can already tell. Multiply the y values by 3. Negative 3, negative, or sorry, 0, and then 3. So those are our values. But since we didn't have a transformation left or right, still it applies that we have the 0.21 on there because of what our base is. Alright. So we have, the asymptote's not going to change. So we have 1/2 negative 3. 1/2 negative 3. 0, 1, 2, 3. Or 1, 0, sorry. 1, 0. Notice that because we didn't have any directional transformations, we still have the same x-intercept as the original. And then we have 2, 3. Because that's what that means. That's why it's a... It did the thing again where it deleted the points. Oh my gosh. You know, I just am starting to get fed up with this app. It seemed good at first. Maybe I can find something else that's better. 2, 3. Okay, so you can see that I will just highlight in red what the original points were. So we had 1/2 negative 1. That's right here. Then we had 1, 0, 2, 1. Same. 2, 1. So we see the 3 red. We see the 3 red ones, and then we see the 3 blue ones, which look stretched, the blue ones. And they look stretched vertically, don't they? That's why it's called a vertical stretch. So hopefully you see that. And now let's graph. And it's even going to go crazy like that and go kind of that way. So that's what that is. Here we have a horizontal stretch because the 3 is in the parentheses. And that means... Yeah, there it goes again, doing that. It means we have a horizontal stretch. No compression because it is greater than 1. And that means x values need to be multiplied by 3. Alright, so y values stay the same. So if we need to have the x values multiplied by 3, we have 1.5 here. We have 3 here, and we have 6 here. Okay? So we have 1.5, negative 1. 1.5, negative 1. We have 3, 0. And we have 6, 1. So notice that we do have a horizontal stretch. But because it was horizontal, that means that we don't have the same intercept. So now we need to fully graph this. So, oh, didn't mean to do that. Okay. And that's what our graph would somewhat look like. All right. Now let's look at our next one. Oh, this looks like it has a little bit of everything. Let's make this 1/2, just so you can see what a compression looks like. Okay, so I'm going to highlight the things that are different from the parent function. We have that, it's different. We have that, that's different. We have that, that's different. And this. So there's 4 things. There is I'll just list them over here. There is a vertical compression of 1/2. And that would mean that we divide the y values by 2, but if you want to keep it common that we multiply them, then we can just say this. That's the same thing. Okay, then we had a horizontal stretch of 3, which means we multiply our x values by 3. And then, I forgot the two other things. Plus 2 minus 1. We have since it's plus 2, that's left 2. And that means x minus 2. And since we had minus 1, that means down 1, which means y minus 1. So those are the 4 things we need to do to the values. So both the x and y are changing. We first need to do the multiplying things, because that's order of operations. So let's start out with doing the x changes that are multiplying. So we multiply the x's by 3. We get this. Okay, let's multiply the y's by 1/2 now. So if we multiply -1 by 1/2, we get -0.5. Then we still get 0 for this. And then we get positive 0.5. So we've only done the multiplication things. Now we need to do the add and subtract things, and they're both subtract. So we have 1.5 minus 2, which is, we change that to -1.5, or 0.5, sorry. Then we need to do 3 minus 2, which is 1. Why do I do 1? Then we have 6 minus 2, which is 4. So that our x values are done. Now we need to subtract the y values by 1. We have -0 or 1.5. 0 minus 1 is -1. And 0.5 minus 1 is -0.5. So those are our values that we need to plot. A lot of 0.5s, not so good, but that's just what we have to do. So there is a lot of transformations on this. This will look quite a bit different from the other one. -0.5. Oh, and keep in mind, since we have left 2, our asymptote changes to x equals -2, sorry. That is our new asymptote. So we can go past the x-axis or y-axis if we want to. So -0.5, -1.5. Okay. -0.5, -1.5. That's actually not even going to be on any of the lines. So that's right there. Then we have 1, -1. Then we have 4, -0.5. So we will draw this and see how it is. It's going to go somewhat like this. Go through those points and then there. So that looks a lot different because we had compressions, stretches, ups, down, or downs and lefts. So that's what that's like. So that's all the graphing, and I just have one more question before this video ends. This isn't a graphing thing. If you have the graph y equals log base 2 of x, which is our parent function, if it was changed to log base 5 of x, what will the 0.21 change to, and what will the 0.42 change to? So our transformation is log base 2 of x changing to log 5 of x. And we need to know what the 0.21 will change to, what the 0.42 will change to. Well, I already told you that whatever the base is what the value is for when there is 1. So since the value changed to 5, from 2 to 5, then we have 5, 1 instead. So we can see 2, 5. Whenever y is 1, that the undo button is really just not working on here right now. I don't know what's wrong with this. But now, what about this? I didn't tell you what happens if there's 2. Do you notice anything? There is, these are doubled, 2 to 4, 1 to 2. Therefore, we need to double these. 1 to 2, still 5 to 10. So that's the answer for this. So that's it for this video. I know it was long, but we didn't need to go through that. And the next couple videos shouldn't be quite as long. So that's it for this video, and thanks for watching, and I'll see you on the next one.